Chapter 9, Section 2 is what we're in. Section 1, if you remember, we did a one proportional Z interval, right? The confidence interval for one proportion and everything. But in 9.2, we're going to learn how to do estimating a population mean, okay? So we're adding another tool to our analysis of data, all right? And hopefully you are making parameters of when to use certain things, okay? For proportion, you're looking at a ratio or the sample size over the or the n, x over the n, right, for the p hat. But for the population mean, we're dealing with just means, okay, and predominantly just the sample mean, all right? So just kind of know that. We'll look at some theory in here, and I'll kind of, excuse me, decipher or explain what we're going to be doing with that, okay? We're going to obtain a point estimate for population mean. Well, we've kind of done that. State properties of a t distribution now. A t distribution is something that we haven't got into, but we're about to. We're going to determine t values. We're going to construct and interpret a confidence interval for a population mean, and then we'll determine the sample size needed to estimate the population mean within a specified margin of error. Very much like what we did on the one proportional Z interval, right? But we're doing it with the population mean instead of population proportion. Now, point estimate is the value of a statistic that estimates the value of a parameter. For example, the sample mean, X bar, is a point estimate of the population mean, okay? If we look at this, there's 17 of these. These are pennies minted after 1982, are made of 97.5% zinc and 2.5% copper. The following data represents the weights, right? We can treat the data as a simple random sample of all of those pennies minted after 1982. Estimate the proportion mean weight of pennies minted after 1982. Well, we can kind of look at that and we can say, okay, the sample mean is, if we just add all of them up and divide by 17, right? 2.464. So the point estimate of the mean is 2.464. Now that's going to be X bar, okay? That's going to be our mean of our sample. So we're saying that you know, when we got looking at these, because of the central limit theorem, it allows us to be able to say that the mean of a population is also correlated to the mean of our samples, right? That there's a distinct relationship between those, and it allows us to be able to do normalizing and different things like that, Z intervals and T intervals, okay? So a student's T distribution, if we were to calculate the T distribution by hand, it would be X bar minus the mean, right? That mean of the population, right? And S divided by S divided by the square root of N. Now, U is mean, X bar is the sample mean, right? And S is the sample standard deviation. So we could come up with a T value, okay? So what does a T value look like? Well, we have T values, right? Let's see if I can bring it up. I think I got it. Yeah, right there. I have a T distribution table. It's the same one that you got in your, when you do that, right? So you're looking at a T distribution. How does that differ from a Z-score, right? Well, a T distribution is a little bit more relaxed. It takes in a lot more area. It includes a little bit more variability, okay? But it also deals with a thing called the degrees of freedom, okay? And we're going to talk about that because we really haven't nailed down exactly what that is, okay? So we've got n is the number, and then the student's t distribution with the n minus 1 degrees of freedom. So I guess degrees of freedom is all, if we look at n minus 1, well, n is the sample size, right? So your degree of freedom would be n minus 1, right? Well, if you were to look at this, let's see, if I took 3 numbers, okay, and we said, okay, if you average those, the mean happens to be 10, right? So the mean is 10, and if you go, okay, that's minus 5, this is 0. How far is it from the mean, right? 5 from negative 10. 5 minus 10 is negative 5, right? 10 minus 10 is 0. Now, we can do this. We know that this number right here is got to be fixed because this sum has to be 0, right? We talked about the deviation away from something, and we add all that deviation up in the residuals, it has to equal 0, right? We talked about that when we were doing linear linear regressions, least squares regression. So if I were to say that the degrees of freedom on this, well, I have 3 samples, so 3 minus 1 is 2. I have, what I'm saying when I say I have degrees of freedom of 2 means that I have basically 2, right? These values can be arbitrarily. They can be whatever they need to be, right? But this last value has to be fixed because it has to be whatever it is to make it to be 0, okay? So it's kind of like, how much variability do you have in play? How much of your variables are able to be varied, right? So if I took a sample of 3, then 2 of my variables would have the opportunity to be whatever they needed to be, okay? That last one would be fixed. So does that give you a little bit more, or maybe a little bit better understanding of what a degree of freedom is? And it's, we're looking at it in n minus 1, right? Because we'll talk about t, when we look this up in it, we're talking about the degrees of freedoms. We're looking at it, the degrees of freedom is the amount of numbers that can vary within your sample, because there'll always be a certain amount that's fixed to make it be 0. Okay, I guess that's best. Yeah, better than just saying degrees of freedom is n minus 1. Okay, so hopefully that gave you a little bit deeper, a little bit better understanding what degrees of freedom is. It's just saying how many of the numbers can be changed in your sample. Okay, and then it tells you how many. And if you have a sample of 15 and you have a degree of freedom of 13, well, you got 2 of them that are fixed, right? You got 13 of them that can vary. That's what it's talking about. All right, so we're going to look at this. We're going to compare a standard normal distribution to the t distribution using simulations, okay? And we're going to look at it in terms of histograms. All right, so here's a z, right? Nothing surprising. The histogram of a z is symmetric and bell-shaped with the center of the distribution at 0, and virtually all rectangles are between -3 and 3, right? In other words, z follows a standard normal distribution, okay? And we've seen that, right? We saw that when you start to increase the sample size, what happens to the sample shape? It becomes more bell-shaped, and the standard deviation of it goes down. So if we look at a t, if you look at this, the histogram for a t is also symmetric and bell-shaped with the center of the distribution at 0. But the distribution of t has a longer tail, Okay, if you can look, you see how things are over here. We got things there, right? It's a longer tail, so it's going to have a little bit more variability. Okay, um, you would prefer on a safe bet, you would prefer a t-test, like t-test, a t confidence interval over a z confidence interval. Okay, because it gives you more of a safety net. All right. So it's unlike the t that follows the standard normal distribution. The additional spread in the distribution of t can be attributed to the fact that we use s, the standard deviation of the sample, to find t instead of the population sigma, right? The standard deviation of the population. So we're using the sample's standard deviation. So that's why it's spread out a little bit more. Because the sample deviation is itself a random variable rather than a constant, such as sigma, we have more dispersion than in the distribution of t, as we would see in a z. Okay, so just kind of, what am I supposed to take from this? Well, you take that t has more variability, it's more spread out over what we just finished up with z, with a one proportional, using a z table and all that other stuff, right? um, we're looking at fixed, right? It's more controlled, it's more precise. And a T is kind of going, okay, I know it's going to be about this, but I'm going to spread it out a little bit, because the standard deviation is not from the population, it's from the sample. So we have a little bit more variability in it. Okay. Now, some properties of T distribution. The T distribution is different for different degrees of freedom, right? Degrees of freedom happen to deal with what number of um, excuse me, in your sample can be varied, right? The number in your sample that can be varied. The T distribution is centered at 0, and it is symmetric. The area under the curve is still 1, right? We have still equal to 1. The area under the curve to the right of 0 equals the curve to the left, so it's symmetrical. So we got 0.5 above it and 0.5 below it. So the empirical rule of understanding how we use the bell-shaped curve is still true. All right. As t increases or decreases without bound, the graph approaches but never equals 0. It just means it continues going out to the left and right. All right. The area in the tails of the t is a little greater than the area in the tails of a standard normal distribution, because we're using s, the standard deviation of the sample, as an estimate of the population's standard deviation, thereby introducing further variability into the t statistic. Okay, so we're being cautious. We're being able to spread out, so we have a wider band, right? As the sample size n increases, the density curve of t gets closer to the standard normal. So if n increases, the curve gets closer, right? This results because the sample size n increases, the values of s gets closer to the population standard deviation. So you start to get less variability as you get closer to your population as n increases, right? And we have seen that, we've looked at that, we've talked about that many times, but it just kind of keeps popping up, just things to kind of be mindful of as we're going through adding new things. Okay, any questions about that? All right, so here's a pictorial representation. The black happens to be a normal. So do you see how the normal is a little bit taller in the middle and it's a little bit shorter on the tails? And then you can see where you've got an N of 15 and then an N of 5. We would expect the N of 5 to go out longer, right? A smaller sample compared to 15. So that's really what they're trying to show there. All right. Y'all good? Any questions on that so far? So all of the similarities between a Z uh, distribution of it, a normal distribution using the Z, we're going to apply to the T, except for we're going to be using the standard deviation of the sample mean, right? All right, the notation T sub alpha, right? T alpha is the um, T value such that the area under the standard normal curve of the right is alpha. The figure illustrates. So we're looking at this. If we say T alpha, we're talking about T sub alpha. We're looking at things to the right. Well, we did that with our one proportional Z test, right? Or Z interval, not test, interval. So we're still going to be doing the same thing, all right? And note that there's still symmetry. You know, when we look at confidence intervals, and we will, um, you've got to make sure that you are um, pulling the right value. Okay, we'll talk about that as we proceed in the homework so that you'll know. Now, you can do this, and I can show you, you know, we can look at it, you know, this is the area to the right of the tail, right? It's the area to the right of the tail. Well, you have to understand that there's symmetry. So if there's area to the right of the tail, all of these are going to be positive, right? But if we're looking for, and that goes up to 100 and 1,000 and then goes to Z, right? Which is what we ought to be. But if we do look at anything to the left, then these are just going to be negative values as far as if they're on the below the mean. If they're on this side of the tail, it's going to be a negative value, right? As opposed to the right side of the tail. We saw that in Z scores, right? So just kind of take that into account when you're pulling your T values from your charts. But I'll show you how to do it on the calculator so that you don't have to pull it. Okay. All right. So finding the T value such that the area under the T distribution to the right of the T value is 0.2, assuming 10 degrees of freedom. That is, find T's 0.2 with 10 degrees of freedom, right? It ought to be, it ought to be of 0.879, right? If we've done it correctly. Well, we're about to use the table, and we're going to see it. And then we're also going to use the calculator to do this a little bit, okay? Because it's a perfect example to do that with. And I can show you both ways. Now, let's go grab the table. We got a 0.2, right, of 10 degrees, right? 0.2 with 10 degrees. So if I can read this, where's 0.2, right? 10 degrees. Here's 0.2, 10 degrees, 0.879. Do y'all see that? This is where we're at right here, right? Everybody with me? We came down to 0.2, and we came over from the degrees of freedom, and where they intersect, that is our T value. Okay? Any questions on that? Anybody? All right. Y'all really quiet tonight. So let's show you how to do it with a calculator. All right, because that's really how you want to know, right? All right, so how do I do this? Second vars, right? Well, they're giving us the area, right? And if you think about when they gave us the area of a z-score, we used inverse norm, right? A number 3. Well, look at number 4. It's inverse t, right? So what we're going to do is we're going to say, okay, we need number 4, which is inverse t. The area is 0.2, right? 0.2. And then we have a degree of freedom of 10. That's all we have to put in there and hit paste, and it brings it to your screen, and then hit enter. And it gives me negative 0.8791. Now, it's giving me a negative. Why? Because it's assuming that we're on the left-hand tail, right? We're on the left-hand tail of that curve. But we actually need the right-hand tail, right? So that's why it's positive 0.8791, right? Any questions about that? Very important little concept right there. You have to know how to read your inverse t depending upon if you're on the left tail, you take it just like it is. If it's on the right tail, then you have to make it positive, okay, because it's going to return a left tail, okay. All right. 1 minus a number. Well, because there's symmetry, we're talking about we're talking about an interval, okay? So we're going to look at confidence intervals using the T table. So we're looking at our parameters of where our boundaries are going to be. So that's why. And it's just giving you the right-hand side. So if I wanted to, you just got to know that you have symmetry, right? So it's a little bit different. Did that make sense? It's 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 not traditionally like a Z per se, like you're reading a Z score, right? Where you've got the stuff, you find it, if you do it on the calculator, it's for the left, and you just change the sign because there's symmetry, right? You're looking at the little small area, so you don't have to do 1 minus if you're using calculator, right? All right. So constructing a 1 minus alpha confidence interval for mean, the lower bound is x bar minus the t score, right? The t distribution score times s divided by the square root of n. And then the upper bound would be x bar, the mean of the sample, plus the t score or t distribution times the sample standard deviation over the square root of n. Okay, so it's just like what we calculated in a one proportional, but it's using different parameters. We're using a t table, right? A t distribution now. Okay. Any questions on that? We can do a confidence interval for mean provided that sample data comes from a simple random sample or randomized experiment. The sample size is relative small to the population size, right? Same as what we've seen on the other confidence interval proportion test we did, or interval. The data comes from the population as normally distributed, or the sample size is large, right? So those are things, still parameters that we got to look at. All right. They're going to look at constructing a confidence interval on this, right? So they wanted a, let's see, a mean of 0.2 grams. So they had a T 99% confident with a weight mean. So if you go, how did they find that T? Well, 99%, right, is basically saying, like what we said before, this is 99%. So this is 0.5% and 0.5%, right? Which is 0.005, right? That's the area here, which would still be the same as the area down here. So does that help with the not having to do the 1 minus? You're looking at a specified area, why it's symmetrical. So if you look that up in the table with a degree of freedom, and they had 17, so it'd be degree of freedom of 16, right? You would get the 2.464, right? Well, the 2.921 here, okay? So now, how would we do this if we were just looking at, if we were looking just to do it on the calculator, right? Here's calculation by hand. You've got that. You can do it. You plug in the stuff, you find it, right? But if we need to do this where it's by hand, well, on the calculator, because, if we don't have to do it by hand, that's great. So if we do it by the calculator, here we go. So we're going to hit stat, right? And we're going to go over here to test. And previously, what did we do? We went to A, right? Because we were doing a 1 proportional Z confidence interval, right? All right. We're not doing a 1 proportional Z confidence interval. We're doing a T interval, which is number 8. Okay. If I hit that, then it gives me two inputs. I can input data, right? I can take the data itself and I can put that in there. Or, the pennies, I could type all 17 of them in there and put it in there and it would calculate it, right? Or I could say, okay, let's do it from stats. If it does it from stats, then it's looking for a couple of things. It's looking for the mean of the sample, the standard deviation of the sample, and the number that's in our sample, the n, and its confidence interval. So once you make sure that you're on stats, if you arrow down, looking at the example that's on our notes, right, we have, let's see, X bar is 2.464, right? Okay. The standard deviation sample is 0.02. Now, they are 17 in our sample, right? Or n is 17. Now, our confidence interval, we want a 99, so it's 0.99. Okay. And if we hit calculate, then we get basically a T interval of 2.4498 all the way up to 2.478, right? And how did these compare? Well, if you were to round to two decimal places, this would become 2.45 and this would become 2.48. Or if we went to 3, I guess, things would round correctly and we would be back sitting here looking at the same things, right? So we can say that we're 99% confident that the mean of the population will fall between these two weights, right? That's what you're doing. Why do you do a confidence interval? You're providing parameters of where things are going to fall. How confident are you that this is? Because you don't want to go out to the population per se, right? You making a prediction with confidence. How confident are you, right? So any questions about how we just did that on the calculator and how they're doing it by hand? Yeah, I did. So let me go back and let me do this. Let me go back and I'll pull up what I had. Let me go here. Oh, no, it's pulling up that. So, all right, so stats, go over here to test, right? We're doing intervals. So for 9, 2, you're going to use the T interval, right? Um, if I hit enter, there's things I've got to put down. X bar, which is the mean of the sample, right? The standard deviation of the sample, the number that's in the sample, and then our confidence level, which is C level, right? As a decimal. Those are the 4 things that I must put in, okay? And those are the 4 things that they're going to provide to you, which is pretty cool, right? Because yeah, if we if if we did a sample based off a study and then we just took a small sample compared to the population, then and we get our sample, we're looking at our data, we can create confidence intervals that say, okay, for projection purposes, the mean ought to fall between these two, the lower bound and the upper bound, right? They do, where they use this the most is what we just got finished with or still in the process with. I don't know. I don't watch the news anymore. Um, with elections, with polling, right? They're polling data, right? They're they're making a projection based off a sample, um, and they're saying, okay, hey, the whole population ought to fall between these. So that's how they're finding, how they're making projections on stuff. Now, the thing you have to be worse and more careful about is how biased are those samples, right? So, did they do a good job of sampling, picking a random sample, or how did they perform their sample from choosing their individuals? So just kind of keep that in mind. All right. All right. So yeah. Okay. You got this. Okay. What you got was this. Let me come down. And what you have to understand is they're rounding, right? So I got 2.4498. Did you get 2.4498? Okay. All right. So let's go over here. If we are to take 2.4498 and we've got to basically to 3 decimal places, right? Which means I have to hold this one and look at this one. This is going to go to 0. This is going to go to what? A 5. That's going to be 4 and 2. There you go. So they just rounded it. And because that placeholder for third decimal was a 9, when you and the number past it was greater than 5 or more, it made it go up to 0, which made your second digits change as well. So that's why it's the same. It just appears or looks a little bit different, right? Yeah. All right. Determinant sample size, right? So we determine the sample size on one proportional Z confidence interval, right? Not anything different. So we're going to look at this, and we're going to actually, when we do the sample size, we're still going to use a Z-score, okay? Not a T, a Z, because they're not going to give us any kind of degrees of freedom or anything. So we can't use a T, right? We have to go back to our Z. So um, the sample required to estimate the population mean with a level of confidence 1 minus alpha times 100% is within a specified margin of error. E is given by this, rounded up to the nearest whole number. So the Z-score of the confidence interval, right, times the standard deviation sample, right, divided by E, the margin of error, squared. So if we look at this, our next example says, all right, so we've got required to estimate the mean weight of how large would a sample need to be required to estimate the mean weight of penny manufactured after 1982 within 0.005 grams. Here's your E, right? That's your error. 0.99 confidence interval, right? So what's the Z-score of a 0.99 confidence interval, right? And then an S of 0.02. Well, if you look at this, we got 99% right here. Then we got a half, correct? So we basically 0. Let's see, 1, 2. Is it? I'm not sitting here doubting myself on this. Let's go 0.05 with my basic math calculations. 1 divided by 2. Well, duh. 0.5. That's why I caught my mistake. 0.5%, right? That's on the tail, which would be 0.12005, right? So we'd have a Z-score, the area, we need the Z-score of the area of 0.005, right? So if we do that, we know we can get that if we do this, inverse norm, right, of 0.005 with a mean of 0 and a standard deviation of 1. We can find that very quickly, right? And if you do that, again, make sure that yours is going to come up saying no tail on that, right? The tail would be always to the left, right? So it comes up with negative 2.5758, right? Okay. So we just, because we're looking at the left, right? So we look at it from a term of absolute because we don't know exactly what, is it right one or left? Okay. So we just need its value. But if you look over here, you can see where these things are plugged in, right? Here's our of a 0.005, 2.575. They just rounded 2 decimal places or 3 decimal places, right? So there's my area, the z-score, right, of that. Here's my standard deviation, and here's my error, 0.005. Do that, and you get 106.09, which goes to, guess what, 107. So the only thing that you really are going to have to calculate is sample size. That's really the only thing you're going to have to calculate by hand, period, in this particular section. That's really the only thing you're calculating by hand in 9.1, right? So just be aware of that, okay? Any questions on that up to right now? Anybody? Y'all good? We found how to do a t-score, so to speak, from a distribution, doing inverse t, right? We've looked at how to do the left bound and right bound of a t confidence interval, and we found what is our sample size got to be based on parameters for a t distribution, right? So there. So that's really the lesson. So again, there's 3 little components. How do I find the t given the area, right? If we're looking at it, we want the t score, t distribution value off of that. Right and left boundaries of a confidence interval based on whatever confidence they give us. And then, of course, the sample. So that's very similar. Matter of fact, it's identical to the 3 things that we looked at for the content that was in 9.1, right? This is doing a T. 9.1 is doing a 1 proportional Z confidence interval, right? 1 proportional. We're doing a mean and using a T. Now, here's some problems off the homework. But before we start that, anybody got any questions before we move on? Yeah, there's 9 people on here. Folks, there's 21 people in our class. You miss out when you just watching the video. You miss out the discussions of, opportunity to have to ask questions and so forth. So thank you for attending. Because you do have that, but it's hard. And I know I'm sending this out, and I know I'm preaching to the choir that's sitting here. All right. So in our homework, it says determine the point estimate of the population mean and margin, right? See this, I got a chat. Yep. Oh yeah, you're exactly right. They do help on the homework as well. So, yep. We're going to determine a point estimate. The thing that they're going to give us is a lower bound and an upper bound, right? So what you have to understand is it's symmetrical, meaning half of it's to the left of that mean, half of it's to the right. So if I want the middle, it says what's the population mean? Well, if I do 16 plus 28 divided by 2, I get a mean of 22, right? It's the middle, right? It's the midpoint, correct? If these are the boundaries right here, then if we're looking at like this, here's 22, right? Now, the next question is, what's the margin of error for this confidence interval? Well, how far is it from 22 to 28? It's 6. And how far is it from 22 down to 16? It's 6, right? And it should be symmetrical. So the error for the confidence interval is 6. Okay, now you could do that. You could go 22 minus 16 is 6, and then 28 minus 16 is 6 as well. You can do it by calculations, or you can draw it out. Either way is fine. Any questions off that? All right, so let's look at another problem, and it picks up right here. Determine the t-value for each of these cases, right? So find a t-value such that the area to the right is 0.25 with 23 degrees of freedom. Okay, now we're talking about the area to the right. So the area to the right would be positive. Area to the left would be negative, right? So let's kind of look at this as we've got a area to the right, area in the right, area on the left, right? Look at its answer right here. Yep. What did I miss? I didn't put the negative there. That's the only thing on that. I just got sloppy. And then we're going to talk about this, finding a critical value, right? That D. Okay, so we can do this. It's all on using a inverse T, right? Inverse T, and we're going to have to put in, let's see. Area to the right. It's this. So they're doing, let's see, I'll work this. It was 1 minus 0.25, right? Comma 23, right? So, and then inverse T, 1 minus 0.05. Oh, I don't need that little, I need this here. Comma 11, because that's the degrees of 11, right? And then this one would just be the inverse T of 0.005, comma 27, right? And so you could type these in, and this is what it's going to be. But we'll do this. Let's see. I want to go back and look at this because I've got some stuff I didn't even look at. So go to that and try it on your calculator while I try it, and I'll show you on mine here in a second. So I'm going to give you about, I don't know, about 15, 20 seconds for A, B, and C. Do that on your own calculator, please. Okay. It's telling it that it's the right side. So that's what you want to make sure. Okay. 7, 9, 7. Yeah. Yep. Let me do this one, and then I'll show you on mine real quick. Bars 4. And it takes a little bit when you do the inverse T. All right. So if you just put it in as 0.25 instead of 1 minus 0.25, then you're going to get a negative value. Okay? That's the only difference. You can still put it in as 0.25 and just know that it's going to give you a negative. Just make it positive. That's all you got to do. Okay? So, or you could put 1 minus, which is going to tell it that you're wanting the right-hand side, which is going to give you a positive. Okay? So, any questions about that? Really, I would probably, think about it now as I'm going back through the third time. I would probably, just do 0.25 comma 23, right? And then take basically the absolute value of it, depending upon what I got, right? The absolute value. And then if it's on the left, I'd make it negative. If it's on the right, then it would stay positive, right? Okay. Any questions off of that? Excellent. Couldn't said it any better. That's it. Now, how do you force your calculator to give you a positive or negative? Well, you put 1 minus that, or you just put the tail, the area, right? And then you just make it positive or negative, depending upon where it's at. Fair enough? All right, so I want to look at this one. Did everybody get those? They're basic calculations, right? It's kind of like when we did the inverse norm. We had the area underneath with a 0 mean and standard deviation of 1, and it would give us the z-score, right? And hopefully you've made a table of your confidence intervals for that for one proportional, so you can grab them real quick. You won't have to calculate them. But I want to look at this part D. It says find a critical t-value that corresponds to a 60% confidence, right? Assume 11 degrees of freedom. Now, what it's saying is, okay, 60% is here, which means that we've got 40%, which would be 20% and 20% on each side, left tail and the right tail, okay, which is, guess what? 0. What? 2. So if we were to do this, the inverse norm, not inverse norm, T would be, well, find a critical. They're looking at it, when they say find a critical, they didn't say left tail or right tail, did they? So if they just say find a critical t-value, then it's going to report it, or you need to report it back as a positive value, right? If they don't tell you what tail it's talking about. So you're doing, excuse me, 0.2, comma, 11, right? And when you do that, you get, if you do this, you get negative 0.8755, right? Okay. Well, of course, guys, I'm just looking, I'm treating it as though it's the left side, right? So do I have to consider that negative right there? This negative right here? No, because it said just find the critical t-value. It didn't say left or right. I just need a t-value to be able to know. I can apply the negative and or the positive to it, depending on where you're telling me it is, okay? All right. So if that's rounded off to 3, then it's 0.876, right? Now kind of treat it like an absolute value, unless they tell you left or right. Fair enough? Y'all good with that? So it's good to know how to do things on the calculator. Now, here's, yeah, it would. Um, yeah, no, it accounted wrong. But I mean, I'd give you back partial. I wouldn't give you back, it for that case, it would be round off errors, right? Um, it would be, you would get back probably about 80%, 85% of your points on that particular problem, right? On that particular little answer. Because, yeah, you knew how to do it. You just didn't know how to represent your answer. So it's the last 10 to 15% of what to do with my answer that you didn't correctly get. Does that make sense? Yeah. So, yep. Good questions. Keep them coming. All right. So let's go look at this one. This one's pretty cool because it gives you the opportunity to do intervals, right? Left bound and right bound. Okay. So we're going to look at this, and we're going to do, I want you to kind of make sure you're aware of some things, okay? So the sample size is n. The mean x is found to be 18.2, right? And the mean standard deviation S is found at 4.9. Because they gave you the standard deviation of the sample, we're going to do a t-test, okay? Because just kind of keep that in mind. So x mean of the sample is 18.2. S is 4.9. Boy, that doesn't look like an S, does it? Let me make it. Let's do S of x, right? And then let's see. We want, okay, it said n is 34, and then we go a confidence interval of 0.95, right? So if we were to go on your calculator and we were to go test, not test, if we were to go stat, arrow over to test, and go down to number 8, right? And we do that and type those in, guess what we're going to get? We're going to get, and I'll do it real quick. We're going to hit, let me clear this out. We're going to hit stat. We're going to go over here to test, right? We're going to go down to number 8, T interval, right? Intervals are confidence intervals, okay? We're talking about the statistics. They gave us an X bar of 18.2, right? Okay. And they gave us a standard deviation of 4.9. And then they said, okay, our sample size was 34. And then we had a confidence interval of 95. All right. Now, everybody good with what we typed in right there? If you hit calculate, hit enter, it's going to give you a lower bound of 16.49 and an upper bound of 19.91, right? It's going to 3 decimal places. They want you to round it to 2. Just know they want it 2, okay? But anybody not get that? You need to be doing this with your calculator, okay? You need to be doing things in conjunction with what I'm doing. All right, so we can take that, and now we just, here it is. The lower bound is 16.49, upper bound is 19.91, right? We do this again with a 95% confidence interval and now an N of 51. So all we're going to do is we're going to come back over here. We'll go to stat. The only thing we got to change is our N, right? We're going down to number 8. I can either scroll down or I can hit it. You got to arrow down. We're going to N. Our N is not 34 anymore. It's 51, right? 51. And then we're standing at 95% confident, right? Interval. Hit calculate, and then we get a 16.68 or 60.822 and 19.578. And if you look at that, they rounded to 2 decimal places, correct? So the only thing that happened different between A and B was the sample size went from 34 up to 51. Now, how does increasing the sample size affect the margin of error? Okay, so you think about, okay, look at my confidence interval. We kept it at 95, right? So I had A was at a sample size of 34, and then B was at a size of 51. Who has a tighter, as we went up in the thing, our bounds got what? What did our bounds do? That's exactly right. Okay, they become closer together because as your sample size increases, your sample standard deviation is approaching the standard deviation of the population, right? So you should start to see the error go, right? So that's kind of what they're wanting you to do with A and B. They want you to be able to see that. So they gave you some problems to do, but they also said, okay, now let's analyze what we just did. What's the effect of changing the sample size? Well, the margin of error decreased, right? It was a tighter band. All right, so on C, they said, okay, construct a 99 confidence interval with a sample size of 34, right? So if you do that in your calculator, and you're going to keep the same 18.2 and 4.9 for the standard deviation of the sample. You're going to have a N now of 34, right? Same as what we had in part A. But the only thing that we're doing, C is changing part A only in respect to the confidence interval, right? Instead of a 95% confidence interval in A with a sample size of 34, now we're looking at a 99% confidence interval with the same sample size. And we get its lower bound and upper bound, right? Boom, not a problem, right? Stats, test, number 8, right? T interval. Compare the results obtained in part A. How does increasing the level of confidence affect the size of the margin of error? the margin of error, guess what? Increased, right? It went out more, right? So D turned around and said, you know what? If we have a sample size of 13, what conditions must be satisfied to compute the confidence interval? Well, the sample data must come from a population that's normally distributed with no outliers because the sample size is so small, right? So they're just kind of some more theoretical type questions. And really, D, you know, what's D really doing? What, you know, they're just dropping the sample size. Uh, and there was a couple more choices that I didn't get when I copied that over. So when you work in your homework on this one, and I think the homework on this one is, well, I didn't grab it, what specific number it was, but you can look at the other choices and then analyze it from there. All right. Any questions about creating a lower bound and upper bound? Uh-huh. Well, your sample size has to be less than 5% of the total population, right? Um, it's really part D is not going to make sense because the other two choices for that particular problem I didn't carry over. So that's my bad. Um, so you're just going to look at the effects of things, right? What's N going to do to it? So it's an opportunity to gather a little bit more understanding by changing some variables in there. Fair enough? Yeah. All right. Good question. All right. So this one, something I did on this one, I actually grabbed it. It's 9.2, number 30, which is so you know exactly which one it is in your homework. Now, my numbers are different from yours, right? So you're going to create, let's see, it says a survey was conducted that asked 1,012 people how many books they've read in the past year. So the results indicated that the X bar, the mean, was 11.6. Standard deviation of the sample was 16.6 books. Construct a 95% confidence interval from the mean number of books people read, and then interpret the interval. Well, we've got, if you do this, right, we're going to do a T interval, right? That's stats. Oh, shoot. Stats over the test, right? And then it's number 8, right? So when you do that, you have the X bar is 11.6 of the mean, right? Standard deviation of sample is 16.6. And then you have, what's my sample size, right? 1,012. And then you have a confidence level, right? Confidence interval. And that particular confidence interval gave you was 0.95, right? And if you type this all into your calculator, what you're going to get is this. You should get a lower bound of 10.58 is less than the mean of the population, is less than 12.62, right? There's a point right there, 12.62. All right, so select the choice below and fill in the answer boxes. Okay, so what does your answer mean? Well, your answer means there's a 95% confidence that the population's mean number of books is somewhere between the lower bound and the upper bound. Okay, so you're making a a prediction, but it's not just a prediction. It's how confident of a prediction is it, right? It's still got error, right? Still got error. I mean, you 99%, you still got 1% error, or 95%, you still got 5% error. But to be 95% sure that it's going to fall between two parameters is very crucial when you're taking a sample size, comparing it back to the population, right? The business world does this all the time when they're doing quality checks, right? You don't want to have to go out and check the whole population, right? You want to be able to check a sample size and be able to say within confidence, where's it going to be? You know, what's my mean? What's it falling in this? You know, how's it compare? So Um, just different techniques that different businesses or different things use math, especially statistics. All right. Any questions on that? Now, I didn't show you how to do it on the calculator, but I read it, wrote it out in red. You ought to know how to get to it by now. I've given you opportunity to do that, right? All right. So one last thing on 9.2, and then we'll go to 9.3. Now, 9.3 is not a real long, but it's packed with opportunity. Okay. So let's look. We're looking at a doctor wants to estimate the mean high HDL cholesterol of all 20 to 29-year-old females. How many subjects are needed to estimate the mean within 2 points with 99% confidence, assuming that the sample standard deviation is 13.6. That's what the S is, right? The sample standard deviation. So it's given us everything that we need, right? Which is cool. Because except for this, now we've got to do, because they're going to say, okay, I want a 99 and a 95, right? So we got to turn around and find out what those are. And if you do, you should know, you do your area, do inverse norm in that, you're going to get a 1.96 for 99% confidence interval with Z-score and a 2.5758, which we have found previously, right? So these things are what you need to make sure that you have in a table so you can quickly get to them, right? So they said, okay, I'm going to do it with the A, with the 99% one, okay? And then I'll write out what the other one is. So we've got the Z-score, for 99 is 2.5758 times the standard deviation, which happens to be 13.6, right? It's the S, all divided by what? Well, your error, and it said within 2, right? Now, when you do that and square it, you come out with 306.791, which goes up to, guess what? 307, right? So that's how you calculate your sample size, okay? Now, I'm going to go ahead and write this out for the 95 so that you can see it when you go back. If the only thing that we're changing is the Z, right? The Z value there. The Z is alpha divided by 2, right? If you look at the formula. And that comes out to be 177.6, which is, guess what? 178. Okay. How does the decrease in confidence affect the sample size required? So if we decreased it, what happened to decreasing the confidence level? Decrease the what? Sample size needed. So if you want to be less confident, then your sample size is going to be smaller, right? If you'll be more confident, your confidence interval needs to be up, and your number that you need to sample size needs to be up as well. All right, that's it. Yeah. No, that's a 2. That's a 2. Yeah, that's a 2. That all came from right here, right? It's the Z alpha over 2 times the S, right? Standard deviation of the sample, right? All over E squared, right? There. That's the formula, right? And these confidence or intervals are coming from a Z-score, right? Good. Yeah. Because see, they didn't give us, we can't do a degrees of freedom because we don't know what the sample is, right? So we can't use a T. That's why we have to go back to a Z for the N on this, okay? Y'all good? Sweet. All right, so that's all of 9.2. Now, let's look at 9.3. 9.3 is basically putting it all together. Which procedure do I use? Which appropriate confidence interval do I use to construct? Well, here's a little flow chart. And you're like, oh my God, I got to do this, got to do that. There's different flow charts that you look at. But I'll tell you, if you're given a proportion, right, or a p-hat, right, then you're going to do a one proportional confidence interval. But if you're given a sample mean, you know, how many of y'all remember this? How many of y'all remember Mr. T? Y'all remember Mr. T? Who is Mr. T? Y'all old enough to know who Mr. T is? The actor was on the A team. He was the wrestling, had all the gold chains, right? Mr. T, don't mess with me, fool. You know, I pity the fool. All that type of stuff. That was some pretty cool lines that he used. But Mr. T, when you looked at him, he was a mean guy, right? So if you think about when do I use a T, you're looking for the what? If you see mean, then you should do a t-test, or not t-test, a t-interval, right? And that works better. It's going to give you a more safer parameter, right? Because as compared to a one proportional z confidence interval, which is, it doesn't, the tails don't go all the way out. There's less variability in it, right? So let's kind of look at this. We'll look at this. There's three problems, right? So I want to kind of look and say, okay, based off what I'm given, what do I do? Well, a simple random sample size of 200 intervals are currently employed, individuals are currently employed, is asked if they work at home at least once per week. Of the 200 employed individuals, 37 of them responded that they did, right? Construct a 99% confidence interval for the population proportion. Well, they told you in this one that it was a population proportion, but how do I know based off what I've read up to right there? If I didn't read past that, would I be able to go, do I have to do a one proportional Z confidence interval or a t-test? Well, guys, what did they give you? They gave you an X over N, right? Which is nothing more than p hat, a proportion, right? Which would be 37 over 200, correct? Right? And we could do the calculations off of that, but we don't need to, because if we do a one proportion Z interval, the things that it's going to ask me is this. It's going to ask me for the X, right? It's going to ask me for the N. And it's going to ask me for the confidence interval. And they're all there. There's the X. There's the N. Confidence interval happens to be what? 99. But I don't put it in as 99. I put it in as what? 0.99. If I do that, which is selection A, right? That's selection A. It's going to give me these boundaries. Okay? Note that it didn't give me a standard deviation. It didn't give me a mean, did it? Okay? So section 3 is a hodgepodge. It's like, which one? Okay, you decide which one you use based off what you're given. And that's what you need to, when you're filling out your sheets or making your sheets, what do I need to put down? What am I looking for? What are they giving me that tells me that I need to use this? And then if they give me this and I know how to use this, how do I do it on the calculator? So those are things you need to make sure that you're secure with, okay? All right, any questions on that? So this right here is basically 9-1, right? One proportional Z interval, boom, and it gives you these, right? Here's your inputs. Y'all okay with that? Mighty quiet. Let's see how many people I got out here in Zoom land. Hey, I got 8 people. Somebody dropped off. Woohoo. All right. Let's look at this one. A simple random sample size of 16 is drawn from a population that is normally distributed. Okay, that could be in a T or a one proportional. The sample mean, boom, right there. I can stop. This ought to be what type of test, or not test, confidence interval. It's a mean, Mr. T, right? Mr. T's mean, right? So you've got what? You've got X bar, you've got S of X, you're going to have to know the N, and then you're going to have to know its confidence interval, right? So let's see. N is 16. The sample mean is found to be 69. Standard deviation happens to be 17. And the confidence interval is what? 0.95. And when you do this, you get this 54.94 for the lower bound and a 78.06. Well, I'm rounding it, right? So what, just in case, I mean, it's kind of said 2 decimals, right? But let me write above it in green what you should have, if you're out to 3 decimal places or 4, depending upon what your calculator set up, then in green is what I got on my calculator. Black is what I have to submit my answers by, right? Okay. Any questions on that? Do you see how to determine which one you use? Yeah? I do what now? No, 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 no. Look at that. What does that say right there? What did I kept saying right there? A one proportional Z confidence interval, right? How do I know it's a one proportional key? Look, there's no mean in here, is it? It just told you how many people it surveyed and how many of them said they at least worked at home, right? They gave you an X. Like I said, X bar. Really, it's X, right? Um, they gave you an X value, a designated point. Well, I say it's a designated point. They gave you a value, and then over in it's a proportion, right? It's p hat, right? Um, so that's a one proportional. That's A, right? Selection number. Okay. This one, look what all they gave you. They gave you the what? There's the key word. Mean. Look at it. They also gave you a sample standard deviation, right? They're going to give you a sample standard deviation. If they give you a sample standard deviation, you're going to do a T test. Okay. Now, look at this one. Um, surveyed 1,002 adults. A polling agency asked, when you retire, do you think you have enough money to live comfortable? Out of 1,002 surveyed, 529 stated that they were worried about having enough money to live comfortable in retirement. Construct a 90% confidence interval, right? Now, just from there, they didn't tell me what the mean was. They didn't tell me what standard deviation was. They didn't tell me what the degrees of freedom was, did they? They just said, hey, we took 1,002 people and 529 of them said this. And that's what the simplistic purposes of a one proportional Z interval, right? Selection number A on your calculator, right? It's an X, an N, and a confidence interval. That's the only thing that you need, right? Now, 529, 1,002, and then 0.9. Okay, and you get these, right? And there's a 90% confidence that the true proportion of worried adults is between these two amounts, right? Okay. Now, that's all on 9.3. So technically, that's it. That's every bit of the homework in chapter 9 done, period. So I want to make sure, want to draw your attention to something because I don't want you to do this and kind of go, well, let me look at some stuff and la la la. Maybe Mr. Palmer didn't teach me this. He didn't say this. Yeah. So let me show you something. In chapter 9, let me hit clear. Hit clear here. Stats. You can arrow to the left. It gets you to the test because it's a reciprocal, which means it just rotates, wraps around. There's two that we talked about. T interval, right, which is 9, 2. That's 9-2's content. And then a 1 proportional Z interval, right, confidence interval. Now, you see this thing right here? You see number 7? What does it say? It's this Z interval, doesn't it? Well, let's hit it. Let's see what it does. Now, look what it gives. Standard deviation, the mean, the N, and confidence. We're not going to do that. If they give us those criteria, then we're not doing a Z interval, okay? You can do a T. So just kind of don't use number 7. Don't go, well, I can do that with a Z. No, you want a T on that, okay? If they say standard deviation of the sample, the mean, you're talking about a T confidence interval, okay? So that's what I want to leave you with. Don't go over here. So we haven't talked about using number 7, right? Because you won't. You're just going to use A and number 8 for chapter 9, okay? Those are 2 things. And the only other thing besides finding some stuff is the sample size in both of those, which are just calculations, okay? So that's it, 9 in a nutshell. You've got coming up, you've got, I think, chapter 8, right? Stuff in chapter 8, test, right? Because you took a chapter 7 that closed last night, right? Is that right? Yay, nay? Okay. Just want to make sure my thinking's right and get that